Hi everyone. Today, two examples applying LeChatelier's principle. First, I have this reaction, 2 moles of sulfur dioxide gas reacting with 1 mole of oxygen gas in equilibrium with 2 moles of sulfur trioxide gas and energy. Because the energy is on the right-hand side of the equation, this is an exothermic reaction. I have 6 different scenarios for us to interpret. So, the system is at equilibrium and we add SO2. Some sulfur dioxide is injected into the system to disrupt the equilibrium. How is the equilibrium going to be reestablished? We have 3 options: a shift left, a shift right, or no shift. When it's about adding or removing something, my tip is add goes with away. The side that we add it to, the shift is away from where we added it. Add away. 2 words that start with A. Add away. And then remove, replace. Remove, replace. You're going to see me pushing to add and pulling to remove something. So let's consider this first part. Add SO2. Add, the shift is away. Or, I like to go like this. I'm adding SO2. Even what does it look like the reaction's going to do? If I force some extra SO2 into it, it's going to shift away from that side. We end up artificially elevating the concentration of SO2, so to return to equilibrium, the shift has to be towards the right. Some of the extra SO2 that we just added into the system reacts with some oxygen to produce more sulfur trioxide. So if we add SO2, the shift is to the right. Add, the shift is away. If we remove SO3, look at my move this time. If I remove some SO3, I'm pulling the reaction towards myself. Remove, replace. If we remove some SO3, it has to be replaced. The reaction will proceed more towards the products. So if we remove SO3, again, we have a shift to the right. Add away, remove, replace. If we add SO3, here's SO3. If I add SO3 in, I'm like pushing the reaction away from it. If we're adding SO3, which is a product, the shift is away. So this time it's a shift left. A shift toward the reactants. If we heat it, it makes a difference that we have an exothermic reaction here. To decide on the direction of the shift, we can consider it sort of like it was a chemical. I can see the energy here. If we heat it, that's adding even more energy into the system. Add, the shift is away. Because the energy here is on the product side, if we add energy to the system, if we heat it, the shift is away. This is a shift left toward the reactants. In addition, though, if we have changes in temperature, that is also going to affect the equilibrium constant. So what we need to think about here is, okay, what would the equilibrium law expression look like? And if we have a shift to the left, if we have a shift towards the reactants, we'll end up with a larger denominator. And a larger denominator means that the equilibrium constant will be going down. With this exothermic reaction, if we cool it, that's like removing heat. We need to replace that heat. So here we have a shift right, a shift toward the products. And if we have a higher number on the products part of the equilibrium law, we end up with a larger answer. The equilibrium constant increases. If we decrease the volume, which means increase the pressure, okay, what we want is a shift towards the side with fewer gas molecules. That's a little bit different from fewer total number of gases. Okay? Here there's 2 different gases on the reactant side and 1 gas on the product side, but it's a little bit more involved than that. The gases here, there's 2 moles of SO2 and 1 mole of oxygen gas. So in total, on the reactant side of this reaction, there's actually 3 moles of gas. On the product side here, there's just the one chemical, the sulfur trioxide. It's balanced with the 2. There's 2 moles of gas. 3 moles of gas on the reactant side, 2 moles of gas on the product side. Decrease the volume, increase the pressure. That's going to cause a shift to the side with fewer gas molecules, which here happens to be the product side. So it's a shift to the right. And the equilibrium constant is not going to be affected. Add away, remove, replace. In terms of identifying what's going on with the equilibrium constant, if we end up producing more products, that makes the equilibrium constant increase. If we end up producing more reactants, the equilibrium constant will decrease. A second example, 2 moles of A reacting with 1 mole of B, both gases. This is an endothermic reaction. We have energy written as a term on the reactant side, in equilibrium with 3 moles of chemical C, which is also a gas. If we add B into this, the shift is away from where we added. If we add B, the shift is going to be to the right. A shift towards the right, a shift to the products. If we remove A, it's like we're pulling the reaction towards us. Remove, replace. Remove A, it's going to be a shift left. Changing the concentration also does not affect the equilibrium constant, so the only thing we need to consider on our answer is it left or right? If we heat this system, this time it's endothermic. The energy is on the left-hand side of the reaction. Heating it, adding energy, add energy, putting energy in, pushes the reaction away. Add, away. So here the shift is to the right, towards the products. And if we end up making more products, the equilibrium constant increases. Kc increases. Just like in our previous example, when we had a shift to the right, the equilibrium constant increased. Here we have it again. Shift to the right, the equilibrium constant increases. In both of those cases, we had more products. If we cool the system down, that's like removing energy from the reaction. Remove, replace. I'm like pulling the reaction here. We have a shift left. Shift left. A shift toward the reactants. More reactants, that's the denominator part of the equilibrium law expression. We'd be dividing by a larger number. The equilibrium constant here decreases. Now when we decrease the pressure, that means increase the volume. We're going to have a shift towards the side with the greater number of gas molecules. But let's consider how many gas molecules we have. On the left-hand side, there's 2 A's and 1 B. So in total, there's 2 plus 1, 3 moles of gas on the left-hand side. On the right-hand side, there's 3 moles of gas C. A total of 3 moles on the left, 3 moles on the right. There is not a greater or fewer, they're equal. So by decreasing the pressure, there's actually going to be no shift. We have equal numbers of moles of gases on the product and reactant sides, so there is not going to be a shift no matter what we do to the pressure or the volume. When we have equilibrium expressions to apply the LeChatelier principle to, we have these 2 big ideas: add, away, remove, replace. Whatever side we happen to be adding into the reaction, the equilibrium will be established by shifting away from that side. Here we added B, so the shift was away from that B. Remove, replace, remove, replace. The actions really help. If we remove A, we have a shift towards the left-hand side. It's going to work the same way when we're dealing with temperature. Think of the energy as like it was a chemical. Add, away, remove, replace. But we have the added complication of having to consider what's going on with the equilibrium constant. If we end up in a situation where we're shifting to the right, making more products, the equilibrium constant is going to be increasing. And the opposite is also true. If anytime we end up shifting left because of a change in temperature, the equilibrium constant decreases. Situations involving volume or pressure, we have to be a little bit conscious. We have to count up the total number of moles of gases, and no shift is absolutely a potential answer. Here we had 3 moles of gas on either side of the equation, so when we manipulate the pressure and the volume, we do end up with no shift. And I hope that helps.